Thanks everyone for being here. So in the first part of this talk, I will talk about the community detection and graph semi-supervised learning problem in multiplex networks, and in particular, we are adapting and creating optimization methods to tackle these problems. And in the second part, instead, is more about collaboration networks between scholars. So they are pretty different. The first one is probably more connected with my PhD in applied mathematics, and the second one to my stay at Indiana University with Santo Fortunato thanks to the AxeNet multinet project. We probably all know that the community detection is one of the most important aspects in network science, since it has been proved that real-world networks have a community structure. And with the community structure, we mean the organization of the nodes of the graph into communities, where in a communities we have a set of nodes that are well connected, and they are instead less connected to the other nodes in the graph. And social communities have been studied for a long time, but they are in many other applications. You can think about proteins interaction networks, where the community can be identified like a set of proteins with the same function within the cell, or in the World Wide Web, pages dealing with the same topic. And the final aim of community detection is to find, in the simplest version, a partition of the graph into communities. Therefore, we would like to have a function that evaluates all the different partitions, and these are the quality functions. And one of the most popular one is the Gierman-Neumann modularity function, that is based on the assumption that a random network merely you take a comparison to your network, a null model, and you have different ways to define a null model, but usually you would like to have as comparison a random network with the same degree distributions as yours. So in this talk, I will refer as the second definitions as modularity function. And in general, high values and positive values of modularity means a good partition. In our case, we want to study this problem in multiplex networks, because recent researches have shown that maybe pairwise interactions are not enough to describe the real world. So on one side, we have hypergraphs where you have group interactions. Instead here, we will concentrate with two multiplex networks, where you have a set of networks with the same nodes, and where each network can represent many of different types of interactions. And we don't allow to have interlayer edges, so nodes connected to different layers. And of course, this brings new challenges to this problem, but also we are able to find some patterns that we would not be able to find just using single layer networks. And one of the main problems is starting already from the definition of communities, because also in single layer graphs, the definition is not really precise, but in multiplex networks is even more difficult. And in particular, in this work, we will look for a partition that is, first of all, total. So each node belongs to at least one community. Node disjoint, so each node can belong to just one community. And the most important characteristic is that we are looking for pillar communities. So each node has to belong to the same community across the different layers. Of course, there have been proposed different methods in the literature for community detection of multiplex networks, and we can broadly divide them into three main categories. The first one are the flattening methods, so they merely just aggregate all the layers in just one single layer, and then they apply usual single network community detection methods on it. The second categories instead are methods which apply single layer community detection algorithms to each of the layer, and then they try to combine the results, for example, using consensus. But these two type of methods are criticized mainly because they don't really use the multi-aspect of the multiplex network, and also they can have good results usually when all the layers are well clustered, not when there is noise, when the layers are corrupted. That's why we are more interested in the third type of methods, which actually operate directly on the multiplex aspect. You can, for example, think a random walker that right now can also walk with the same probability to another layer and not just in the edges of one layer. And in particular, in our method, we would like to simultaneously optimize the modularity of all the layers without aggregating the different networks. And the two reasons why we wanted to propose a new method, maybe I already told them. So the first one is that we don't want anymore to have a method that can be just with the informative cases, so when all the layers are well clustered, but also in the noisy cases, so where some layers are noisy, because we know that in a real application this happens. And the second reason is that almost all of these methods needs to have as input the number of communities, and in a real application this is an assumption that we need to do because we don't have this information usually. Our method is an extension of the popular Louvain heuristics for single layer graphs. This is a method that is composed by two phases. So in the first phase, each node is inserted in a community and is considered one by one, and the node is inserted in the community that gives the highest increase of modularity. And this first phase is repeated until the methods converges. So until moving just one node, you cannot have an increase of modularity. And in the second phase, mainly the method constructs a reduced network. So each community becomes a supernode. And you apply the first phase to this reduced network. And you repeat these two phases until the method converges. So until in the second phase, you don't always find the same network. And it is pretty popular also because it is quite fast. And the reason is that for each step, you don't have to calculate the increase of modularity from zero, but you have an incremental way to calculate it. And this is very important from the computational point of view. So we would like to extend this method to multiplex networks. So we don't have anymore just one graph, but a set of graphs. And we don't want to optimize anymore just a modularity function on that graph, but a vector of modularities. And because, for example, a partition can be very good for one layer, but very bad for another one. So we want to optimize them simultaneously. And in order to do so, we write this problem as a multi-objective optimization problem, where we want to optimize this vector of modularities over all the possible partitions. But we know that if we have k layers in Rk, there is not an a priori total order. So there is not a unique definition of optimal. So we decided to use as the optimal definition according to Pareto, that says that if we have two vectors in Rk, the first one dominates the second one if all the coordinates are higher, and at least one of them is strictly higher. And according to that, you can say that a vector is Pareto optimal if no other vector dominates it. And at the end, you have a set of these points, probably not just one, a set of these points, and you call it the Pareto front. That are the set, so the points that are not dominated by the other ones. And in our method, we would like to go and investigate these Pareto fronts. So it is very similar to the Louvain heuristic. So at the end, each node is inserted in a community, and it is also inserted in all the possible, all its neighbors. So you have a set of all possible partitions that is a set of all possible, the corresponding vector of modularities. But you don't keep all these long list of set vector of modularities, but just the one that are not dominated. That's why this is called a filter type method, because you filter out all the modularity vectors that are dominated. And you keep going to do that until the method converges. So until the final list of vectors does not change. And then you go on with the second phase, creating a reducted network like in the usual method. The problem is, of course, that doing that, this list can, even if you have just points that are dominated, can increase exponentially, because in the second phase, you should keep all of them, equator, das network, and so on. So what we did was to, at the end of the first phase, you just keep one or two of these vectors that are the best one according to some functions, just to handle the length of the list. And we studied 3 different functions to handle the length of this list of vectors that are not dominated according to Pareto. The first one is to consider simply the modularity average. And but then on the other side, we wanted also to try to take into consideration also of the variance of the modularities across the layers. So we took a convex combination between the average and the variance. And in particular, we used the first convex combination for the informative case, because we would like solution with a high average modularity, but also a low variance of modularities across layers, since they are all well clustered. But on the other side, in the noisy case, we would like a high average modularity, but also we would like also solution with a high variance, since some layers can be corrupted, so noisy. And I just want to say that these functions, first of all, can be calculated in an iteratively way, like in the original heuristic. So computationally, it's a fast method, let's say. And on the other side, I just want to make it clear that we are not optimizing this function. We are doing a multi-objective optimization, and we are using this function just to handle the length of the list. Otherwise, would be not manageable. And we tested our method over different synthetic data sets and real data sets, but here I'm going to show just one result, where we pick a real data set, the 3-source data set with that has 3 layers. And on the columns, we are adding from 1 to 5 layers of completely noisy. And in the rows, we have the different methods. The first one are our methods that use the different f functions with the length of the list equal to 2 and 3. And then we have below the other methods that we compare to from the literature. And we can see that our methods, especially the ones that use also the variance in addition to the average of modularities, can achieve high values of accuracy and NMI, even in the case where we are adding many layers of noise. Okay, my second project was pretty close, because it was about the graph semi-supervised learning problem, that we still have a graph. We still want to find a partition of the graph, but in this case, we have some input labels. So we know the community of some of the nodes. And from the structure of the graph, we want to learn the partition. Therefore, the problem seems quite similar, but the techniques involved are quite different. So what people usually do in the literature is to, for each class, so in this, usually we call it class, but it's the same as community in the first project. People for each class optimize this function that is composed by 2 terms. The first term is a fitting term. So we would like the variable x that is our prediction of the nodes to be closer to the input labels that we already know, the nodes that we already know that are in that class. And the second part instead is a regularization term. So mainly if we have an edge between 2 nodes, we will like their probability to be in the same community high. And lambda is just a regularization term. So after that you minimize this function for each class, you will have a solution, a prediction for each of these class. You will simply insert a node in the class with the highest probability. So what we would like to do is to extend this method to multiplex networks. So like before, we don't have anymore just one adjacency matrix, but we have a set of adjacency matrix, one for each layer. And what people usually do in literature is to assume that we have, in the informative case, so all of the layers are well clustered, and so they take either the average or the union of them. But in real applications, we know that we can have some completely noisy layers, or each layer can just bring partially the information that we want about the community. So the idea would be that we would like to give to each of these layers a different weight, but we don't know this weight a priori, so we would like to learn it from the input labels that we have. And in order to do so, we consider this weight, the generalized mean adjacency matrix, that is mainly a linear combination of the adjacency matrix of the multiplex, and then there is also a parameter alpha to have also not linear combinations. And the reason why we decided to study exactly this weight is because for particular values of alpha and beta, we can retrieve, for example, the one that I said before, so just the average of the union of the layers. So it's something like an extension of the methods that are usually used. But as I said before, okay, this is the weight that we would like to use, but we don't know it. We have to learn this parameter alpha and beta. And that's why we write this problem as a bi-level optimization model, where, so in the lower level, you are simply minimizing the function of the single layer graph. You are just using this weight that we have seen before. This is the lower level. But in the upper level, instead, we are optimizing these alpha and beta, so the weights that we want to give to the different layers. And we are using H, that is a cross-entropy loss function. And also, we also decided to optimize lambda with alpha and beta, just that is the regularization parameter, just to have at the end a zero parameter method. So the fact is that you can like or not this formulation, but usually in bi-level optimization, it's difficult to actually at the end solve the problem, because mainly you are optimizing a function that depends on the optimization of another function. So usually it's not easy, but in this case we were pretty lucky, because we can solve the lower level problem exactly using label spreading. So mainly you set the gradient of the function to 0, and you discover that the solution is a solution of a fixed point equation. So in practice, you just need to run some iteration of this fixed point equation. So when you have the solution of the lower level problem, you can insert it in the upper level. And to solve the upper level, if we look at the feasible region, it is a quite simple one, because alpha and lambda belong to boxes, and beta belongs to the unit simplex. So we decided to solve this problem using the Frank-Wolf algorithm. If you don't know much about the Frank-Wolf algorithm, simply it is an heuristic that at each iteration solve the linearization of the function. So if you solve the linearization of the function over a box, you just need the sign of the derivative. And over the unit simplex, you just need the gradient. So it's really fast and simple. Of course, actually, we don't use exactly the Frank-Wolf algorithm, but we use it with an approximation of the gradient, because in practice it's too difficult to calculate. So we use the finite difference method. And therefore, we also needed a result about the actual convergence of our method. So under some assumption about, of course, the function that we are optimizing and the feasible region that we have in our case, we can see that our method has a sublinear convergence rate, where, of course, the constants depend on the quality of the gradient approximation. And we tested our methods over 3 different synthetic settings. The first one, where we have 3 layers that are all well clustered. The second setting, where 2 layers are completely noisy. And the third case, where each layer brings some information about some partial information. And on the upper level, we try to optimize 2 different cross-entropy loss functions. I'm saying that just because that's why in the results I will show 2 different versions. So in the first one, we are optimizing a cross-entropy function for each classes. In the second one, just one multi-class cross entropy loss. And looking at this example, beta are the weights that we are giving to the 3 different layers. And we can see that in the informative case, the method seems to give the same importance to all the layers, since all of them are well clustered. In the second case, it's able to understand that just the first one is actually well clustered. The other one are just noisy. And in the third case, the complementary one, it's able to give a higher weight to the first layer, first cluster in the first layer, second cluster, second layer, third cluster in the third layer. That's what we wanted, our intuition would want. And also comparing our methods to the one that just take the average or the union of the layers and other 4 methods from the literature, we can see that our methods can achieve higher results in these 3 different settings. And we also tested them over different real-world data sets, adding 1 or 2 layers of noise, and we could still see the same good results, that they can achieve higher values of accuracy. This is the second part of the talk, and it's more about the application of the science of science. Yeah, it's not, if you are thinking where is the connection, I think that there is not a real connection, so, okay? And so the science of science, mainly science can be described as a complex, evolving, multi-scale network, and the science of science wants to find patterns that characterize the structure and evolution of science, with the final aim of accelerate science. And the dataset that we are using in this project is OpenAlex. It is completely free, and it is quite recent, so every month they release a new snapshot where they can probably change something regarding, for example, the disambiguation of authors, or how they handle affiliations and so on. So if you want to talk more about these datasets, I'll be happy to. And in particular, we work with collaborations between scholars, because collaborations are a key driver of science and innovation. And thanks to collaborations, scholars are exposed to new tools and theories, and collaborations also facilitate the diffusion of ideas. And one way to study collaborations are collaboration networks, where the nodes are the researchers, and 2 researchers are connected if they wrote at least 1 paper together, and the weight of the edge will be the number of papers that they wrote together. And collaboration networks have been studied quite a lot, so we know a lot of properties of them. And we can see also collaboration networks as a manifestations of homophily, because of course, if some researchers are interested in the same topic, probably they can team up and work together. And on the other side, we can also see that they could also induce a social influence, because if a researcher likes a topic and work on a topic, can induce another one of his collaborators to work on it. And that's why we can see it also like a social contagion process, where an author that works on a topic influence another one to work on it, and that's why epidemiological models has been also used to model the diffusion of ideas. And in this talk, when I say that there is a topic switch, I mean that a scholar start to work on a completely new topic. And our main object is to study this interplay between collaborations and topic switches. And I want to say for now that, of course, in this work, we can only measure the effects of collaborations on topic switches, and we cannot establish any causal relationship. So our methodology consists in, we pick a topic, we pick a start here, and we created 2 time windows, one of 5 years before and one of 5 years after this starting here. Of course, then the results will be also across different topics and across different years. And using these 2 time periods, we will identify a set of active authors. So the active authors are all the authors who wrote at least one paper in the topic in the first period. And then looking at the other papers still in the first interaction window, we can create their collaboration graph. So mainly in this collaboration graph, we have some active authors who wrote at least one paper in the topic in the first window, and some inactive authors who are their collaborators. They wrote some papers together in this window, but not related to the topic. And what we want to do is to see in the second window how many of these inactive authors start to work on the topic. And we take into considerations the two complementary point of view, so the point of view of inactive authors and the point of view of active authors. So from the point of view of inactive authors, we define as contact the number of papers that this inactive author wrote with the active authors. And of course, they have to have written a paper not in the topic, otherwise they will be active too. And when we do so, we want to calculate the so-called membership closure, so the probability that this inactive author becomes active as a function of the number of contacts. And in order to do so, we calculated the target activation probability, that is the fraction of inactive authors who became active with more than k contacts. And if we look at the results of 6 sample concepts, we can see, first of all, that this probability is increasing. So it seems like that highest is the number of contacts, highest is the probability for an author to start to work on that topic. Second, we see the highest increase in the for k equal to 1. So it means that having at least one contact can make the difference with respect to spontaneously start to work on a topic. And then we also compare our results with a simple baseline, where we suppose that each contact is independent. And we can see that the plot do not match. So it seems like that pairwise interactions are not enough to describe these events.
These are not the topics. This is the area.
These are the concepts. So the topic.
This is the topic. So
yeah, the topic.
I'm a bit lost on how you define a topic.
In the OpenAlex datasets, you have a system of concepts that is a tree. So you have like the concepts at level 0 are very broad, like mathematics, medicine, and then you go down in the different levels. These are level 2 concepts for OpenAlex.
And T0 is when it has been defined for the first time.
No. T0 is you simply in the results we are averaging across different T0, and T0 is simply an year. So you just say, I have this topic, I don't care when was born or when ended. We just pick a time, and we look of the authors that were working on the topic the 5 years before, how many of their co-authors would work on it the 5 years after. And then we are changing this T0 and averaging the results. It's not connected to the initial date of the topic or something. And then in the second part, we are looking from the point of view of the active authors. So considering an active authors, we want to know how many of his inactive collaborators became active. And then we are also, we call this the source activation probability, and we are also interested in the chaperoning propensity. So how many of these actually wrote their first paper with that author? So that connection was really important for them to actually start working on that topic. And in order to do so, we calculated the cumulative probabilities. So we look when these fractions are higher than a certain threshold. And our main assumption was that we wanted to know if when an author is more prominent, according, for example, to productivity or for impact, this author has a higher probability to influence his co-authors to start to work on a topic. And in order to do so, we rank the active authors according to productivity and impact, and we analyze the difference between the most and the less prominent authors. And from these results, we can see that they are actually significant because all of them, unless 2 for impact, do not cross the 0 lines and are all positive. So it means like that this is true. Seems like that if an author is more prominent, this author has the highest probability to influence his co-authors to start working on a topic.
The productivity is just the number of papers.
Yeah, the productivity is the number of paper and the impact is the number of citations. Yeah, that's why we also are less sure about the impact, because it involves citations and probably open access is less good with respect to just productivity. And the final thing that we wanted to look is that if there was also something connected to the team size. So our idea was like that if an author writes paper with a lot of co-authors, maybe there is something like a dilution effect. So it is less probably that authors will influence many of them. So we ranked the prominent authors according to the team size of their papers. And we could see that actually we can see a dilution effect. So it seems like that if a prominent author writes a lot of papers or has a lot of citations, but these papers has a lot of authors, this effect is, it has a less effect to influence the co-authors to start working on the topic. And then the last project is one of the projects that I'm also working now with my lab, and is about how the COVID pandemic influenced collaborations between scholars, because we all know that COVID changed our daily routines, limiting our social interactions, and there has been some research about the importance of in-person interactions in the fostering of ideas. So that's why we wanted to analyze in particular how the COVID pandemic had an effect on how scholars collaborate, so how they started new collaborations, for example, but also if a little bit of also if this had an effect on the final papers. We are still using the OpenAlex datasets, but since we want to do a transversal analysis month by month, we don't really can trust much the publication dates of OpenAlex. So we decided to restrict ourselves to the archive by archive and meta-archive datasets where we have the publication of the preprints. Also because we know that from when you start a new collaboration and you have your paper published, there can pass a lot of time. So also to consider the preprint publication date for us made more sense to see the effect of collaborations. So the first thing that we looked at was the productivity before, during, and after the pandemic. So in dotted lines, there is March 2020 that was supposed to be the beginning of the pandemic. And we can see that there was an increase of productivity during and also after the pandemic. We are restricting to preprints, so it can also depend on how much these platforms were used. And if we look at the COVID preprints, just to have an idea, this is in logarithm scale. So right after the pandemic, we have a big peak of COVID papers that is slowly going down till today. And the first assumption, the first intuition for us was that since researchers could not meet at conferences or at universities, maybe it was harder during the pandemic to create new collaborations. And in order to study that, for each month, we created a collaboration graph of that month, and we subtract the collaborations that were already in the past. So we end up with the actual new collaborations, so with the collaborations between authors that never collaborated before. And in particular, in this case, for example, we would consider just one of these edges because A5 is a completely new author, and therefore, of course, a new author will bring just new connections, and we don't want to take account of that in our analysis. And this was the result, and it was quite surprising because it seems like that not only we have less new collaborations, but it seems like that there was an increase of new collaborations. And this plot is fitted with a piecewise polynomial. So the breakpoint is it is due to the minimization of the square errors. And it seems like that there was a change in January 2021. As I said before, we are not surprised by the fact that it's not at the beginning of the pandemic, because when you start to collaborate or write or work on a project, probably you will publish some months or years after. And so this was very surprising for us. And we started to understand more about some characteristics of these collaborations.
Is this just for the COVID paper?
No, for all the papers, everything. Yes. Preprints, restricted to the preprints. So we started to understand more about some characteristics of these collaborations, and especially if they were between people of the same institutions or not. So we define a collaboration as intra-institutions if the two co-authors are in the same institution, and inter-institution otherwise. And we could see that after the pandemic, there was an increase of collaborations between different institutions. And also, if we look at it, we still have this effect in this change of behavior in 2021. And our assumption is that since during the pandemic, researchers had to work remotely, both with people from the same of different institutions, that could have incentivized people to work with people from other institutions, even far away, and with maybe different skills. And then we decided then to look more deeply about the actual distance of these institutions, not just if they were in the same or two different institutions. So for each paper, we took the average of the distances of the team members. And also this plot, I would say that it seems pretty clear. So it seems like that there was an increasing trend before the pandemic, but it got even more. The team average distance, it seems that increased much more after 2021. And still this is probably connected with the people working more remotely, so don't really care much about how far away is the other collaborator. And finally, the other thing that we did was, following a paper published in 2012, to project the collaboration networks to the institution networks. So for example, here we have 4 authors from 3 different institutions. It will be a click. And they split the weight 1 between the different edges, and they discovered that this weight follow gravity law, where the mass is the strength of the institutions, and then you have this, the power is not 2, but is a different, can be a different alpha. So we tried to reproduce that with our data sets, and we could find the same power law, likely. And we tried to look at that for 4 different periods. And the most surprising things was during the pandemic, so the pink line. It seems like that we had a higher propensity to work with university far away, and especially this line is parallel. So it seems like that there was an increase that was independent of the actual distance of these institutions, and this is still in line with remote collaborations. And right now, what we are doing, that is for me the most interesting part, is that we are trying to create a model that could actually explain this and reproduce this behavior to better understand it. But the second part of this project is about that, okay, if we believe that the pandemic brought a change in how researchers collaborate, did this have an effect of the final paper that they published? So we are analyzing different measures to understand that. And right now I'm just showing the simplest one, that is the impact factor. So we are just counting the number of citations of papers after 1 year. The first thing that we can see is a big peak exactly at the beginning of the pandemic. And this can probably be explained by the early mover advantage, because here we have the number of COVID preprints that has a peak right after the pandemic, and then the impact factor of COVID preprints. So it seems like that the very early papers about coronavirus were very highly cited by the big amount of papers published on COVID the months after. But the other interesting part is what happened after the pandemic, because it seems like that there was a decrease of impact. And maybe it's not so surprising if we think that there are already some papers, some research published about the fact that remote collaborations can bring less creativity. So that's what we would like to analyze better. These are the, in conclusion, in this first part of the talk, we have seen the community detection graph semi-supervised learning problem in multiplex networks with some optimization formulations and tailoring and adapting some optimization methods to solve them. So I think that the most important thing is that when we have a multiplex networks, we cannot simply aggregate all the layers or take their union, because there can be like noisy and corrupted layers. And in the second part of the talk, we have seen a bit about collaboration networks, in particular topics which is in science, seeing that how prominent a person is or the number of contacts with active authors can have an effect on the probability to start working on a new topic, and also about how the pandemic changed collaboration networks between researchers, making them more interinstitutionally, but that this had also an impact on the final papers. I want for sure to thank my collaborators, because of course I'm not the only worker of these papers. And thank you all of you for listening and being here.
I have a question.
Okay.
So in the citation project, so that app, when you have that like nice distance plot, like a big change in the distance between collaborators, I'm wondering if you did this analysis as well as like the previous slides analysis with COVID versus non-COVID papers. Because my intuition tells me that like the COVID research, like all the data was scattered all across the world, and so you are forcing people to interact from like researchers in China or researchers in other like countries that were generating data. So just forcing them into distance.
I think that we have some, for sure, now I don't remember, honestly, because we did different things, and every time, of course, we want to know if this is concerning just the COVID papers or all the papers. Right now, honestly, I don't remember, but for sure, it would be important also to look at this aspect. Because also, there is also this thing that every time we also note that the size of collaboration has increased in time. So in this case, we are normalizing, but of course, sometimes COVID papers are in medicine, and in medicine, usually you have much more people inside the team. So yeah, there are multiple aspects to take into consideration, but thanks, we will surely do that.
Yeah, I think really more than all the papers versus the COVID paper is indeed the non-COVID papers versus the COVID paper that
yeah.
You don't have an analysis separate.
I didn't put everything, yeah. But for example, here you can see that if you don't have COVID papers, you don't have this peak, but you still have the decrease.
Yeah.
So the COVID papers had an effect close to the pandemic, but then it seems like
you should definitely distinguish, because what happened during COVID is that the COVID paper bench was something that is completely insane and not. Yeah, even in terms of impact, those kind of things on the impact. At certain point of COVID, there was so much trash that I would say, yeah. Overall, I don't understand why you find this surprising, because the hypothesis would be natural. In a sense, we all learn that we need on Zoom. And so the barrier that we felt probably before the pandemic to initiate long distance collaboration after 6 months of pandemic, 7 months of pandemics was not there. People started to work. So I would expect actually this. Why
We
start
did-
from the position?
So we did not expect it because to have a new collaborations, you have to actually meet that person. To meet them, you have to go to conferences or visiting another institutions. So you have to actually have an occasion to meet that person.
Yeah, but indeed, we had 2 years of remote conferences. So we were going to remote conference. So we learned how to live out, I would say, out of the real world.
Yeah, probably. Yeah, the results probably are in that direction. So yeah,
It's the natural
response.
take is
Okay.
the opposite. I
Mhm.
would have expected something. Please.
And the question, like, so it's interesting to see the shock, like COVID pandemic. Like, have you more results on that? Also, like the recovery part, like as the system kind of got back to normal in the sense of like now are we kind of like not that we're used to kind of like being this virtual world and being able to interact at great distance. Like,
Yeah. I think that it would be really nice to do this study after some years because right now we are still disconnected. We still have sometimes, like, for example, for the impact factor, you need at least 1 year ahead to take the citations, but we also know that preprints usually get more citations when the paper is actually published. So yeah, I think that for now we can just trust till 2022. But yeah, in the future it will be interesting to see if people keep working remotely or not, if this actually had a change in effect.
go ahead. It's another question to another paper to look at. The one that you see that, like, with when you have like this nice curve of like the adoption curve for the computing process. Actually, how do you generate the simple baseline? Do you do
Yeah, I think that I have a slide because it's easier to. This one.
Do you try to fit this P value?
Yeah, it's very simple. So P is the probability of activation from a single contact, and we take it from the observed from the data, and then the probability of the baseline is simply this one. So if you have K contacts and you assume them to be independent, this is the probability.
So you take what is N1 over N1?
I think that from the results, using the first point, you decide the probability, and then you use that.
Here's to kind of like, if you have any hypothesis of like, is this simple confusion?
Yeah, that was really super simple. Like, let's take like baseline, like assuming that they are all independent and there is no fitting, but probably one should investigate more deeply to better understand how it actually goes. Also because we know the collaboration networks probably are more like can be represented by hypergraphs, more group interactions. So it's not so surprising probably that pairwise interactions are not enough. Thanks.
My takeaway was combination one that you were saying that people are more productive if they're long distance collaboration and producing more papers, also, but that they're somehow less creative. Am I reading that correctly?
So about the more productive, I'm not sure because there are also more researchers. So if you have a plot also of the number of the researchers, this one is increasing too. And on the other side, yeah, less impactful, it seems so. It seems like that remote collaborations create less creative, produce less creative papers. And there are already 2 works about that.
That makes sense. A little bit disappointing, right? Like we're collaborating with more people, but it's less important.
Yeah.
Maybe it is important.
That's why we would like to better understand if this actually an impact.
This again is for all papers.
All papers. And if you don't have the COVID papers, you don't have the peak, but you still have the decrease. The impact factor, we are simply calculating the citations of these preprints 1 year after their publication.
So only 1 year after.
Yeah, because otherwise we would not have enough years after.
That is an effect of the fact that I don't know, it's because you wanted is that you have much more paper, something happened there that was drastic, and then you, in a sense, the number of citations. I don't know.
Because there is also this thing that there are more papers, but also if you plot the average number of references, it is increasing too. So of course, if paper also have more references, there is higher probability to be cited, but there are also more papers. So yeah, that's it.
So another question.
Please, I'm just clarifying. In slide 24, what is that?
It's just a terminology when you have an optimization problem. You have a function to optimize, and then you have some constraints. And you call the region defined by these constraints the feasible region. That's only a definition. Yeah. So you want the parameters to be, yeah, in this region.
Last question. Like, how do you quantify the belonging? Was the one on the first slide, the belonging to the region? How do you quantify that?
You mean in the real data sets? So in the synthetic data sets, we created the data sets, so we know the right partition for us, let's say, and the ground truth. These are real data sets, but of course they are not. They also give you some partitions, some good partitions. So to calculate the accuracy, of course, we needed the ground truth. We are using a ground truth. I don't know if I answered the question. So there are some data sets that you can find online, and you have the multiplex networks, but you also have a ground truth with that. So for example, 3 sources is a data set with 3 layers concerning papers of 3 different journals, and they manually pick a label to each of these papers, like it's about sport, it's about something else, and then you have this partition. Of course, we cannot say that is the best partition and so on, but we use that one for calculate the truths. Yeah.
Going on the topic switch, I'm a little still puzzled by this. You use this very high level, there are different topical levels that you can define, because there is, you use different categorization. You stay at the very high level.
Yeah.
So like dark matter.
Yeah, we have more of them. These are just 6 examples, but yeah.
So I'm wondering how many actual people are not in one window and then working. So dark matter is so vast that are they switching to cryptography? No, I think there is something that is, how is it possible? So if you look into your T0, how many authors really are publishing outside of that broad area? And how many people you have in the statistics? Because my guess is that that's small numbers, very, very small numbers. Have you?
I mean, we have also some about the number of. We have a slide to have an idea about the number of papers and authors that we are considering. Yeah, this is the number of papers and authors. So the number of T0 that we are considering for each of these topics, and for the 2 windows, we have the number of papers published and the total number of authors. We have.
The interaction window, you have 8,380 authors.
So this is an average, of course, because we are considering 13 different.
Those authors have published in things which were not dark matter, or in the interaction window. What?
I think that the number of authors is the number that I don't remember if it's the number of people in the collaboration networks that we create, of the people, but no, I think that is the number of people that wrote in dark matter in the interaction window. So I should have another number to understand how many people are in the network.
Yeah, because I expect that there were few, so I can't imagine how many people are authoring a paper are not authoring.
Yeah, I got the point.
And then jump to that matter later, because the field is so big. I would understand if you have a final graining. I'm doing astroparticles, and then I jump into from gamma rays to beta bugs. You know, this is the things. You are in statistical physics. You go from spin glasses to label propagation. But how many people who are in statistical I don't know, they do networks and goes into that matter. I think 4 or 5, 6. So this is to wonder your statistics when you do
sure.
Network, how much they are. When you have an error bars associated.
Yeah. I mean, I'm sure that there were some people, because I don't have the results now, but for sure there were none, like 2, 3. Okay. But yeah, I got the point. So it depends on how many level 2. Yeah.
When you have like those probabilities, I'm wondering what is the error bar there? Because you have a small sample.
Okay.
And then is this over what years? You said it's multiple, it's multiple time windows, but what's the time range?
So the methodology is always the same. So we pick a time, and then we take a window of 5 years and 5 years. And we just shift. We pick different T0s. But
What's the earliest possible period?
For example, like in COVID, I read papers from astrophysicists who studied, I don't know, the universe, who decided to write.
Yeah,
we have another project about that. There were people starting to work.
Everybody that was able to deal with an Excel file and an equation that was.
Yeah, we have this Yeah.
That's a different story. I think here is.
It was not concerning COVID. We stay away from COVID. But yeah, that's a good point too.
How do you choose the points about or let's improve that? Like, how many times does relevant words appear in that report?
We are simply using OpenAlex. So for each paper, we have